my favorite part in chemistry is the branch of thermodynamics that deals with the heat absorbed or produced by a chemical reaction. And you know that a chemical reaction can be either exothermic that release energy or endothermic that absorb energy. So first question is, why do chemical reactions occur? The answer is stability. For a reaction to take place spontaneously, the product of the reaction must be more stable than the reactants starting. But what is stability? And what does it mean to say that one substance is more stable than another? Okay, let's think. The most important factor in determining the stability of a substance is the amount of energy it contains. Highly energetic substances are generally less stable or more reactive, while less energetic substances are generally more stable and less reactive. We will explore some different forms of energy in this chapter focused on thermochemistry, which is the absorption or releasing of heat that accompanies a chemical reaction. And so if you're talking about this, the first thing that we need to think is energy. So even though chemistry is the study of matter, energy affects matter, right? So energy is the capacity of or potential to do work or transfer heat. Work is a force acting on an object over distance. Energy used to cause an object that has mass to move. And heat is the transfer of thermal energy. So energy used to cause the temperature of an object to rise. Energy can be changed between objects through contact, for example, through collisions. You can think of energy as a quantity an object can possess, or as a collection of objects. You can think of heat and work as the two different ways that an object can exchange energy with other objects. So we have different forms of energy, and one of the most important here is the kinetic and potential energy. So potential energy is the stored energy that we have in chemical bonds, for example. It's the energy an object possesses by virtue of its position or chemical composition. It's like the food you eat. So when you eat food, what happens? Happen is you have energy to transform that energy and kinetic energy. So you can walk. So that is motion of particles. So kinetic energy is the energy an object possesses by virtue of its motion. And we have thermal energy, which is the energy associated with the temperature and is a form of kinetic energy and is related to temperature. This electrical and potential energy over here depends on the Coulomb constant, the charge, and the distance of separation. So we're going to talk more not in details over here, because here the most important part is to understand the concept, the difference between potential energy and kinetic energy over here. So here we have a high potential energy in this first picture here, where the girl is on her bicycle, and then she come down over here. So it start decreasing potential energy and increasing kinetic energy. So let's think about food that you ate. So you eat because you need energy, right? Of course, some people would say that I eat because I love food, but it's a necessity. You need energy. So when you start moving, like can be talking, thinking, walking, running, working, you start spending those energy. So the food that you ate is the potential energy. So we have energy in your body, and then you start working. So your movement. So that is motion of particle. That is kinetic energy that convert this potential and kinetic. So you can have energy to walk, to run, to think, and to work, right? So that is the way. So we have many forms of energy, like mechanical, and we have chemical, we have electrical. So energy capacity. So it's energy is capacity to do work. We know that we have kinetic energy, potential energy. What's chemical energy? Chemical energy is associated with position of electrons and nucleus. Okay, and we talked about that in part of the previous units. You're gonna remember when we talk about the jump of electrons and different levels of energy. Remember that, right? So units of energy. Historically, energy was measured in units of calories. A calorie is the amount of energy required to raise 1 gram of water by 1 Celsius degree. So, don't get confused with the calories of your food. That here, calorie is capital C, or large calorie, commonly used quantifying food, energy content, right? So that 1 calorie is equal 1,000 calories. So it's important to understand this difference over here. Let me just try to get my pen. Just 1 second. So I will grab my pen over here. So it would be better to explain to you. Let me see. It's not working. No. Oh, here. So let me get my pen. So here I'm gonna explain better for you. So if I have 1 calorie, now again, give me just a second, this disappear. So when I have here, okay, so no, it's not working. Should work, no, yeah. So 1 calorie with caps letter is equal 1,000 calories. Let me just erase over here. Sorry, is equal 1,000 calories, or 1 kilocalorie, because you know that kilo is 1,000, right? So normally we use in an international system for heat, work, energy, we use joules. Joule is defined as the amount of energy used when a force of 1 Newton moves an object 1 meter. It's named in honor of the English physicist James Prescott Joule. 1 calorie is 4.184 joules. Okay, so it's important to understand the units that we're gonna use over here. Don't get confused with 1 calorie with the caps letter with the calorie that we work and the energy. Okay. So thermodynamics is the study of energy and its interconversions. The first law of thermodynamics is the law of conservation of energy, right? So when a chemical energy is in a broken bond is released, it won't be created or destroyed. Heat is so will just be converted in another energy. Okay, so that is conserved. We can change form, like heat energy that involves when the chemical reaction happens. Can be come from broken bonds, but will be converted in another type of energy. Okay, so the total amount of energy in the universe is constant. So we don't produce more than we have. So it's a conservation of energy. Okay. Therefore, you can never design a system that will continue to produce energy without some source of energy. So despite the quantum mechanical exceptions, energy is conserved. So conservation of energy requires that the sum of the energy change in the system and the surrounding must be 0. Okay? Delta is the symbol that means change, so the final amount and the initial amount. So when you say that energy cannot be created or destroyed, which is the first law of the conservation of the thermochemistry, we are saying that when energy is transferred between objects or converted from one form to another, the total amount of energy present at the beginning must be present at the end. So conservation of energy means that the amount of energy gained or lost by a system has to be equal to the amount of energy lost or gained by the surrounded. Like here with the ball, the girl is pressing ball down. So now I have potential energy, so mechanical potential energy, that will be converted in kinetic energy, pulling the ball, pushing the ball to up, right? So the law of conservation of energy during a chemical or physical change, energy can be neither created or destroyed, although its form can change. So, like I said before, energy can be converted from one type to another. Remember the girl on the bicycle? So the potential energy was converted to kinetic energy, movement. Okay, so the energy stored was converted to movement. So you need to understand what is the system and what is surrounding. So the system here, for example, includes the molecules we want to study. Like here we have hydrogen and oxygen inside of the cylinder. The surrounding are everything else around. So the cylinder, the piston over here. So the energy can enter or leave the system as heat or as work done on the piston. It can go up or it can go down. Matter cannot enter or leave the system here, so it's a closed system. So system, we can transfer heat and work, okay, with the surround. So it's a exchange with the surround. So thermal energy is a type of kinetic energy associated with the random motion of atoms and molecules. Again, we are talking about motions. Okay? Temperature is the quantitative measure of hot or cold. When I say it's hot outside, so we need to quantify that. We are working with science. So we need to quantify. And how are we going to quantify? Using the temperature. When the molecules are fast moving, so what do you have? A high thermal energy because they are fast, right? So we have a hot temperature. So it's hot. It's low moving molecules, so we have low thermal energy. So they moving like slower, right? So very is low. So we have a cold. The molecule here have a hot, so the red one, and we have the blue, which is cold water. So heat is the transfer of thermal between two bodies at different temperature. Heat flow, a redundant term but only commonly used, increase the thermal energy of one body and decrease the thermal energy of the other. When two substances are placed in contact, thermal energy will always flow from the high temperature substance to the low temperature substance. Heat flow will continue until both substances are at the same temperature. We call thermal equilibrium, like in this example over here. So we have hot and we have cold. So the transfer will be from the hot to the cold. That is be spontaneously, okay? So then they get a contact, so the transfer will be happen until they get the same temperature over here. So the same average kinetic energy. And this study of the heat absorbed or released during chemical and physical change is the thermochemistry. So remember that I said at the beginning, a reaction can either be exothermic, releasing energy, like we have here with the flame, and can be endothermic, that will absorb energy over there. So a change that releases heat is called exothermic process. For example, the combustion reaction that occurs when using oxyacetylene torch. So we're gonna have heat, so we are releasing heat. Or a change that absorbs heat is an endothermic process. And the heat that we use kill to represent heat is positive. So the reaction, a cold pack used in treat muscle strains that will exchange heat with your body, right? Or the ice over here that is absorbing heat to change the state. So, and this it's important to understand the difference between heat and temperature. So heat is the exchange of thermal energy between a system and surrounding, while temperature is the measure of thermal energy with a sample of matter. And this is how thermometers work. So when two substances are at different temperature and placed in contact, heat flows from the hotter to the cooler one, right? This continues until both reach the same temperature. Remember that I talked about the thermal equilibrium? So that is the principle what makes thermometer reliable. They reach equilibrium with whatever they measure. It can be the air around the thermometer or inside of a reactor, measuring the temperature of a solution or the reaction. Okay? The internal energy that we have with the substance is the sum of kinetic and potential energy, okay, of all the particles that compose of the system. The change in the thermal energy of a system only depends on the amount of energy in the system at the beginning and the end. So a state function is a mathematical function whose result only depends on the initial and final conditions. This is why here and the internal energy change will be equal the internal energy of the products minus the internal energy of the reactants. So in accord with the law of conservation of energy, the total amount of energy in the universe is constant. So the conservation of energy requires that the sum of the energy change in the system must be equal to the energy surrounded, must be zero. Okay, so if you sum of both, the total must be zero. So the relationship between the change in internal energy, heat, and work is summarized in the first law of the thermodynamics. So that the variation or the change in internal energy will be the sum of work and heat. And the energy can be transported in the system, resulting in increasing internal energy. So the system will absorb, so it will be positive, like here in the ice, so that will be the positive one, or can be negative, so that when they release energy, okay, because they're decreasing internal energy. Okay, remember the ice is absorbing heat, so they're increasing internal energy because they're absorbing energy. So the surround do work on the system, but energy can also be transferred, like in here in the heat, so they are releasing heat. So the internal energy is decreasing. Okay, this is important to understand. So when the system gains thermal energy with positive, the system loses thermal energy. When work will be negative, right? When the work done on the system, so then we have positive. But when work done by the system, so it will be negative, like the fire. So they are giving away the heat. Okay, so the change in internal energy. So yeah, internal energy also can be represented by E. Okay, so delta E will be the change in internal energy. To understand better what is the state of function, let's look to this mountain over here. So we have two trails to reach the top. So the long and winding, or short but steep. Regardless of the trail, when you reach the top, it will be 10,000 feet above the base. So this state of function, change in altitude depends only on the difference between the initial and final values that we have over there, not on the path taking. Okay, and we have the energy diagram. So when you have the system, it's losing heat, so it's giving away the heat, so energy will flow from the system to the surrounding. So the energy in the system will be negative, like we have with the fire. So when you have, see that the energy will go from the reactants to the product. When you have the surround is giving heat to the system, the system is absorbing energy like the ice. so will be positive. Okay, so this is just to highlight this part. When you have heat, when we talk about heat, we have something that we call heat capacity of a body of matter. Is the quantity of heat that absorb or release when they experience a temperature change of 1 Celsius degree. The heat capacity is an extensive property, and it's important to understand. Let me grab another pen over here. Oh, sorry. Imagine if I have a cup of water here. Okay, so I have water, and in this side, what I have is a swimming pool. Okay, full of water in a sunny day. Okay, so we have a swimming pool over here, so a lot of water over here. So this one over here will warm up faster than the water in a swimming pool because I have more quantity in the swimming pool, right? So that is heat capacity. So we have the heat by the delta T. So the heat capacity of a large cast iron pan is greater than the heat capacity of a small cast iron pan. And it's important to understand that. So the quantity here will matter, right? But this is why when chemistry, we're going to work with the specific heat capacity, which commonly called specific heat is the quantity of heat required to raise the temperature of 1 gram of a substance by 1 Celsius degree. So in this case, doesn't matter the quantity of the water. Can be in a swimming pool or it can be in a cup of water. So if you both have water, same substance, they will have the same specific heat capacity because we are divided by the mass. Okay, so this part here is good to explain why when you go to the beach, like in a very sunny day in the morning, like at 12 for example, and you are walking in the sand and say like I can barely walk in the sand because it's so hot. But when you get to the water, you feel the water remain colder even in scorching summer noon. Why? Because the sand has a lower heat capacity. That means that will absorb or lose energy really fast. Okay? So to understand that better, let's look to this table over here. So measure of a substance's intrinsic ability to absorb heat. So if you look here, the metals, see how low they are compared to the water? That means if it's in a hot day and I have swimming pool and we have some bunch of metals and you touch the metal, will be so hot because they will absorb heat faster because they have a specific heat very low. Look at the water and the sand. Remember that I gave you the example of the beach? So walk in the sand or going to the water. So look at the water is 4.18 joules per gram Celsius degrees. Remember that is the heat divided by mass and we have the temperature. So that's why it's joules per gram Celsius degree. So sand is 0.84, very low specific heat capacity compared to the water. This is why sand will be so hot faster, like first, so we get hotter first. And also will be the same at night. So the temperature low, it will be lower. So the sand will get colder faster than the water because the specific heat capacity. Okay? Here is more table with the specific heat. So you need to keep in mind that when you have a substance with low specific heat, its temperature increases more quickly when heat is added. And because of this, we can calculate the heat. Because remember, the specific heat that we use CS to represent is the heat divided by mass, delta T. So if you isolate the heat, you can calculate the heat. So if you have the specific heat capacity, you can calculate the heat. If you have both and the temperature, you can calculate the mass. If you can, you can work with the formula. Remember, the delta T is the final temperature and the minus initial temperature. We represent by TF, Ti is the initial. If a substance gains thermal energy, so the final temperature will be larger than this initial temperature, it will be positive. If the lose thermal energy, it will be negative. Okay, heat will be negative. So here I have an example for you, just to see if you understand the concepts. So identical amounts of heat are applied to 50 grams blocks of lead, iron, and copper, all at the initial temperature of 25 degrees. Which block will have the largest increase in temperature? So we have here the specific heat for each of the materials. Look at this. What's the lowest specific heat? Copper, iron, or lead? Okay, lead, right? So which one block will have the large increase in temperature? Lead, because it's lower specific heat. For now, that's it. That's all. Don't forget to watch the second video, where I will solve some problems of heat with you. So you can calculate heat, or you can calculate final temperature. Don't lose that. So that's it. That's all.